Good day everyone, I am Gayle Baturiano and along with my groupmates Jen Baes, Avaseia Danga, Gabriel Inserto, Clemente, Magat, and Paolo Vargas will be discussing one of the most widely known thought experiments in physics revolving around the world of quantum mechanics, Schrodinger's cat. Now let's delve deeper into this thought experiment. Suppose a cat is put inside a box, isolated, with a radioactive material, a flask of poisonous hydrocyanic acid gas, a Geiger counter, and a hammer. If the atom decays, the Geiger counter ticks and triggers the hammer to break the vial of poison, thereby killing the cat. However, if the atom does not decay, then the cat remains unharmed. Until the box is opened, we don't know for sure what state the cat is exactly in because the radioactive atom has a 50-50% chance of decaying. This uncertainty presents itself for both the atom and the cat. As the atom becomes a superposition of a decayed and undecayed atom, the cat also becomes a superposition of a dead and alive cat, meaning that the cat is theoretically alive and dead at the same time. It is important to note that this is not a real experiment. Simply put, this thought experiment was devised in 1935 by Erwin Schrodinger, an Austrian physicist who laid the foundations of quantum wave mechanics through his wave equation, as a way to demonstrate the complexity of quantum physics and the difficulty with its interpretation. He sought to convey that applying the principles of quantum mechanics to macroscopic systems leads to strange consequences, like a cat being simultaneously alive and dead. As such, Schrodinger's cat proved itself to have profound implications in physics and philosophy, emphasizing the principle of superposition, sparking debates on various interpretations of quantum mechanics, making its way to modern technologies, and now has also been used as a powerful tool for discussing ethical dilemmas.
Quantum mechanics, the science of the incredibly small, explores particles like electrons and photons that exist in unpredictable probabilistic states. One of its most famous illustrations is Schrodinger's cat, a thought experiment from 1935 by Erwin Schrödinger. This paradox highlights the strange nature of quantum reality, where observation collapses probabilities into one outcome. It forces us to grapple with questions like, does observation create reality? And what does it mean for something to exist in multiple states at once? This paradox remains central to debates about how we interpret the quantum world, from superposition to entanglement to the nature of consciousness itself.
The problem of Schrödinger's cat is based on the principle of superposition, which is the idea that a system exists in all possible states up until the moment it is observed. Superposition happens when the total state of a system is the combination of each possible state and is only destroyed when observation occurs, making our measurement fall to one of the possibilities, also known as basis states, that form the entire superposition. This concept can be seen in the double slit experiment, wherein electrons pass through two narrow slits and eventually end up on a screen after traveling through some space. As it travels, there is no certain way to tell where it is in space, only where it probably is. This is an example of quantum uncertainty. We can't say for certain that an electron is in X or Y, so we say that it is in both X and Y. The sum of all these probabilities will be the superposition of all the possible paths it could take. When we add up all these paths and probabilities, the paths of electrons will resemble a wave, and it is only when we observe the electron hitting a single random and definite point on the screen that the superposition is broken.
We can use this principle of superposition to explain quantum entanglement. Now, imagine a variation to the scenario wherein you now have two boxes with two cats and the same setup inside. The outcome would be four possibilities. 1. The cats are both dead. 2. The cats are both alive. 3. One cat is dead while the other is alive. And 4. One cat is alive while the other is dead. However, only two of the outcomes here are actually possible. Quantum mechanics tells us that the first two possibilities can be removed from the superposition state. This is because these states are not part of the entangled system's wave function. We are then left with two possibilities. It's always that one cat is alive while the other cat is dead. Physicists refer to this as entanglement, wherein the states of the cats are entangled with one another. Opening one box to observe a cat's fate immediately collapses the wave function for both systems, meaning the death of one cat immediately determines the survival of the other, regardless of how far they are from each other, even if they're put light years apart. Einstein referred to this as spooky action at a distance. The measurement doesn't cause one's cat's state to change the other's. Instead, their states are intrinsically correlated from the moment they become entangled. Measurement merely reveals these correlations. Quantum entanglement challenges our classical understanding of reality by demonstrating how two systems can remain deeply interconnected, regardless of distance.
Schrodinger's thought experiment caused a paradigm shift in how experts view the quantum world. That is, it effectively conveys how paradoxical it indeed is. Schrodinger's cat is said to be alive and dead unless one opens the box. That established, how does the cat cease being alive and dead and offer a singular state upon observation? This points to the measurement problem: how do possibilities become realities? Standard quantum thinking says observing, i.e. opening the box, collapses all possibilities into one reality. Still, how does looking at the cat decide its fate? Is it the observer's consciousness, or is it something else? This brings us to decoherence, wherein systems interacting with their environment lessen their quantum strangeness, almost as if they're classical counterparts. In the experiment, the interaction between the system, i.e. the radioactive atom, and its environment blur quantum effects, much so that one does not notice them. To the observer, the cat is alive or dead, although quantum mechanics state otherwise. Now, here's the catch. Decoherence does not solve the measurement problem. It does not account for how possibilities transform into realities. Instead, quantum strangeness only becomes invisible. It is like mixing two immiscible liquids, oil and water. Decoherence is analogous to someone dimming the lights, much so that the liquids appear as one. That is obviously not the case, but one's impaired vision would have them believe so. This aside, other attempts at resolving the measurement problem are as follows. First, the Copenhagen interpretation. This states that the particle exists in a state of superposition until observation. The cat is alive and dead in the experiment. Lest the box be opened. That act consolidates the possibilities into one outcome: the cat is alive or dead. Criticism: this interpretation does not explain how observations cause possibilities to collapse. Second, many worlds interpretation. This states that every outcome of a quantum event happens in its own universe. That is, opening the box doesn't cause a collapse of possibilities. Rather, it separates them into distinct realities, wherein the cat is alive in one universe and dead in another. Criticism: this interpretation creates an uncountable number of universes and is impossible to prove. Third, Bohm's hidden variables interpretation. This states that factors unaccounted for decide the outcome, guiding quantum events deterministically. For instance, the cat is a gene encoding for radiation immunity. Hence, it survives the experiment no matter what happens. Criticism: this interpretation introduces forces at play that one does not detect.
Next, we have macrorealism. This states that only microscopic entities are quantum and macroscopic entities are not. The animal is alive or dead the whole time. However, evidence suggests that quantum effects can scale to larger systems, invalidating this strict dichotomy. Lastly, we have statistical interpretation. This states that quantum mechanics predict outcomes for larger groups, not individual events. If one repeats the experiment with a million cats, half will be alive and half will die after an hour. However, the interpretation does not address what happens in a single event.
Quantum mechanics is basically saying that nature is probabilistic. In the thought experiment, when the box is closed, the cat is neither dead nor alive. It also does not mean that the cat is both dead and alive at the same time. Rather, it's in a quantum superposition of being dead or alive. And it's only when you open the box that the state changes and you find out whether the cat is dead or alive. Thus, quantum superposition only happens in microscopic levels where there are no interactions happening. However, we live in a world where there are so many interactions. So how significant will the concept of superposition be? Consider an electron going around a nucleus and another nucleus comes by. By then, the electron can choose to orbit around nucleus 1 or nucleus 2, both of them or neither. But the electron will not do any of these since the electron will be in a quantum superposition of orbiting both nucleus 1 and nucleus 2 in an orbital. This superposition is keeping the nuclei together, creating a chemical bond, which is what we call the covalent bond. Without quantum superposition, there wouldn't be any bonding between anything at a molecular level.
So for the real-world implications, we have quantum computing. Quantum bits or qubits can exist in multiple states, such as 0, 1, or both, simultaneously. Akin to the cat being alive and dead, this superposition enables quantum computers to process vast amounts of data simultaneously. This can be applied to making accurate climate change and weather forecasting, drug development and discovery, artificial intelligence, healthcare, and more. Quantum cryptography. The principle of observation affecting a system, like opening the box, underpins a quantum encryption. If a quantum key is intercepted, the act of observation alters its state, making tampering detectable. This can be observed in securing financial transactions with and in between banks. Medicine and imaging. Superposition concepts inform technologies like quantum sensors used in MRI machines and other imaging techniques, enhancing sensitivity and accuracy. Decision making under uncertainty. The thought experiment is metaphorically applied in decision making and risk analysis. Until a decision is made or more information is obtained, all outcomes remain possible. And lastly, philosophical and ethical dilemmas. Schrodinger's cat is often used to discuss issues where multiple truths or outcomes coexist until a definitive action or decision is taken, such as in legal, medical, or ethical contexts.
In summary, Schrodinger's cat thought experiment remains fundamental in understanding the paradoxes of quantum mechanics, particularly the concept of superposition and the role of observation in determining reality. It allows the dynamic interplay between quantum and classical physics, as well as science and philosophy, sparking debates through interpretations like Copenhagen and many worlds. Initially a critic, it has influenced modern advancements including quantum computing, cytography, and medical imaging. Despite its complexity and criticisms, it serves as a powerful tool to explore reality, measurement, and decision-making in uncertain scenarios. That's all for this presentation, and thank you everyone for listening.